Hello, this is Simon from Reigate Maths and welcome to another video for the second year A-level maths content focusing on integration. This video is going to focus specifically at looking at areas of parametric curves. If you don't remember what parametrics are, go back and watch the video that we've provided on parametrics and potentially parametric differentiation as well, because the processes are similar. Hopefully you remember from the first year content how to find an area of under a graph. So if we have a graph, some function y equals f of x, and we're finding the area between these 2 points a and b, we find the area in this way. The problem with that when we get to parametric curves is this, because we have x is defined as some function of t and y is defined as some function of t. I'm sorry for using f twice, but this is a new question. The area, we're still going to integrate between a and b. The area is still going to be y dx, but the problem is that y is in terms of t, so we're trying to integrate some function in t with respect to x. What we would love to be able to do is change the dx to a dt, or just stick a dt on the end. That would be great, but we can't just do that. How do we now alter this section so that the equations, or the things we're trying to calculate, are in fact equivalent? Because currently these are not the same. Or to make it the same, we need to figure out how we can cancel out the dt. And we do that by putting a dt on the denominator. Now if you look, we can now see we have our y function multiplied by our derivative of the x function integrated with respect to t. This entire thing here now only contains t, and so the integration will work. The other problem that we have are the limits. This a and b are for x. So we need to work out functions or our limits in terms of t, which is not too difficult to do. We're just going to stick our x limits in our equation here and solve it. So we're going to have t equals p and t equals q. Okay, and that's how we're going to integrate parametrically. Now if obviously we're not finding an area and we're just integrating parametrically, then we don't need to worry about the limits. But for now, this is a much more general statement. So this is the example we're now going to look at. This is a passable drawing of this set of parametric equations. The graph shows when x is cos 2t and y is 2 cos t and y is sine 2t, and we're going to try and find this shaded area. So we know that the area is the integral of y with respect to x between, we can see, 0 and 2. Okay. Now obviously this is parametric, so we need to do a little bit of work first. So we need dx by dt, which x is cos 2t, so this is minus 2 sine t. And these are also the x limits. X is 2 and x is 0, so we need to change those into t's. So we're going to set x equals 0, x equals to 2. The other way we could do it is set y equal to 0. And then check that those values work in our equation, which thinking about it, that might actually be an easier way to do it, because we can see this is where they cross the x-axis, so y is 0. So when y is 0, sine 2t equals 0, which we know we have many solutions for. 2t, 0, pi, 2 pi, and so on. So t, it's going to be 0, pi over 2, pi, and so on. Now obviously we want to pick which pair is going to be easiest, because the thing with sine and cos graphs or parametric graphs in this, each of these areas is going to be the same size. So if we can find this one, which when t is 0, x is 2, so this is where we start. Then when t is pi over 2, x is 0. So our graph is going in this direction. Then when t is pi, x is minus 2, so we're coming this way, and so on. So we can see that this is the interval that we're interested in. But in reality, you could pick any pair. We're going to choose this one mainly because it's got 0 in, and it gives us exactly this area. But if we were finding this one, for instance, we could use these limits again, because it's probably the same. It should be the same size because of the symmetry of this graph. So now we've got all that, we can stick it all in our equation here. So we've got between 0, when this is the other thing you've got to be careful of as well, is the order. So when t is 0, x equals 2. So when x is 2, we've got to put the 0 on the top, so it fits. And when t is pi over 2, x is 0. So we've got to make sure those are the right way around. Don't panic that this is not your familiar order of limits for integration. In reality, the order doesn't hugely matter in terms of the actual process of doing it. It's just, it might change the sign of the answer, or it will change the sign of the answer. But that's okay. So we're going to put everything in now. So we've got y times dx by dt times dt. It's important that we put this step because it shows the examiner you know how to use the formula. So make sure you put it in. So we got sine 2t times minus 2 sine t times dt. Now this is what we can do with the limits. Because we have a minus now, if we multiply the whole thing by minus 1, we're allowed to swap the limits over, which in reality gets rid of this. So let's do that. So that's 0 pi over 2, 2 sine 2t sine t. The next thing that we need to worry about is how to integrate this thing. Because these two functions, although they're both sine, aren't really linked to each other in a way that we can integrate. How you have to integrate this function is we need to think about our double angles so that we can get it in a reverse chain rule type of form. So two times 2 sine t cos t times sine t dt. Tidying all that up, I'm going to stick the 4 on the front to get that out of the way. And we end up with cos t times sine t squared, or sine squared t. This is now in the reverse chain rule form because the thing on the outside of my bracket is the derivative of what's inside. So this is just going to integrate to 4 times a third sine cubed t which we're going to evaluate between pi over 2 and 0. This is the other reason for using these numbers. It makes our answer really nice and easy to deal with. So I'm going to take the third out so I don't have to deal with that until right at the end. So I'm going to have sine pi over 2 cubed minus sine of 0 cubed. Sine pi over 2 is 1, sine 0 is 0, so this bracket is just 1. And we get 4 over 3 as our answer. And that's how parametric integration works. Typically, it will be this type of question where you have to find an area, because otherwise there's no real point. But it's this bit that you need to be really careful of, is finding the limits. Because a lot of this type of graph has this repetition idea, you might have to be working out different areas from the graph. So you might have to pay attention to which limits work where and how to find them. Typically with trig, the important thing is to not just consider principal value, secondary value, but to consider all of the possible values that you could have and check them in your other variable. So we used y as 0 to work the t values out, and then we tested them in x to find which ones worked with the points we wanted. So that's something you need to be really careful of when doing these questions. Obviously, we could have found the limits out the other way by setting x equals 2 and then solving to find t, checking it in the y, x equals 0, solving to find t, checking it in the y. The order of that doesn't matter. Pick whichever one you think is going to be easier to calculate, and you're away. So hopefully that should be enough for you to go away and practice. Depending on which textbook you're using, which exam board you're using, this may or may not be emphasized particularly strongly, this particular topic. At Reigate we use Pearson. And the first printing of the Pearson textbook didn't have this in, so they added it as extra pages in the back, so it might not be exactly where you expect it to be. So in your textbooks, just make sure you go and find it. If not, if you can't find it and you want more practice, look up old Edexcel Core 4 questions, because it used to be on that. But thank you for watching.